In this lesson, we're going to prepare for working with partial derivatives by looking at functions with multiple variables. Let's consider functions of several variables. We'll start with a function w, such that w is a function of multiple variables, x sub 1, x sub 2, x sub 3, up to x sub n. So our function w, let's move that up, is a function of n different variables, x sub 1 through x sub n. Here, x sub 1 through x sub n are our independent variables, and w is our dependent variable. Our independent variables here are our input variables. These are input into the function, and our dependent variable w is our output variable. Here, w depends on our different input variables. Our input variables are our domain, and our output variables, w, is our range. If our function is a function of two variables, we generally use x and y, and we call our function z. Let's move that up. So in this case, our domain, x and y, represents a graph in two-dimensional space. And z gives this graph a third dimension, a height. If our function is a function with three input variables, we generally use x, y, and z. And we have our range be a different variable, let's say w. Let's move that up. Here, our input variables, our domain, is a three-dimensional space graph. Here we have a function with three input variables. We evaluate functions by substituting the values of the independent variables into the function. For example, let's say that our x variable has a value of 3, our y is 0, and our z is 4. So we're going to substitute these into the equation. And what do we get? Well, we get f of 304 is equal to the square root of 3 squared plus 0 squared plus 4 squared, and that is equal to the square root of 9 plus 0 plus 16, and that is equal to the square root of 25 which is equal to 5. Let's put a box around our final answer. That's the value for the function when x is 3, y is 0, and z is 4. Let's take a look at domains and ranges. In defining a function of more than one variable, we follow the usual practice of excluding inputs that lead to complex numbers or division by 0. Let's look at the function f of xy is equal to the square root of y minus x squared. In this case, the radicand, y minus x squared, must be greater than or equal to 0. This is because we can't take the square root of a negative number unless it's imaginary. So in this case, if we add x squared to both sides, we get y is greater than or equal to x squared. And let's move that up there. Here, our restriction on y is that y must always be greater than or equal to the square of x. Now let's take another function where our function f of xy is equal to 1 over x times y. And in this case, our denominator here, x times y, cannot be equal to 0. So we say that x times y cannot equal 0. The domain of a function is assumed to be the largest set for which the defining rule generates real numbers, unless the domain is otherwise specified explicitly. The range consists of the set of output values for the dependent variable. Here we have the function z, which is equal to the square root of y minus x squared. In this case, the domain is y must always be greater than or equal to x squared. That is our domain restriction. And our range is that z will equal all values, including 0, up to positive infinity. Here we have another function z, which is equal to 1 over x times y. In this case, our domain is that x times y cannot equal 0. Otherwise, we'll have a divide by 0 error. And the limit on the range is that z can go from negative infinity to 0, not including 0. It will never equal 0. And, this is a union, it will also be all values greater than 0, not including 0, up to positive infinity. Note that we have parentheses when we're talking about infinity in our interval notation, here, and also here, because we never reach infinity. When we have a bracket, that means we actually reach that value. Here we can equal 0, and in this case here and here we can't equal 0 because of the parentheses. Here we have a third function, z, which is equal to the sine of x times y. In this case, our domain is the entire xy plane. And the range is limited to all values from -1 to +1. And in this case, we are including, because of our bracket, -1 and +1. Here we have a function w, which has 3 input variables. W is equal to the square root of x squared plus y squared plus z squared. In this case, the domain for this function is the entire 3-dimensional space, x, y, z. So it's the entire 3D space of x, y, z. And the range is that w can be all values, including 0, and up to positive infinity. And of course, we never include infinity. Here we have another function, w, which is equal to 1 over the sum of x squared, y squared, and z squared. In this case, the domain is all values for x, y, and z except when x, y, and z are all equal to 0. Because when they're all equal to 0, we will have a divide by 0 error. So to write this properly, we would say that the point x, y, z in three-dimensional space will not equal the point 0, 0, 0. And the range will include all values from 0, but not including 0, to positive infinity. And that is because w will never have a value of 0. And here we have a third function, w, that's equal to x times y times the natural log of z. In this case, z will never equal 0 and will only be positive. So the domain restriction is that z will always be greater than 0, and the domain restriction, w, will consist of all reals from negative infinity to positive infinity. And again, we note that we use parentheses when we're talking about positive and negative infinity because we never reach them. A point x0, y0 in a region R in the xy plane is an interior point of R if it is the center of a disk of positive radius that lies entirely in the region R. A point x0, y0 is a boundary point of R if every disk centered at x0, y0 contains points that lie outside of the region R, as well as points that lie inside the region R. The region's boundary points itself need not belong to the region R. So in this first case, our point x0, y0 is an interior point. And in our second case, x0, y0 is a boundary point. A region is closed if it's made up of all its interior points, points that are on the inside of the boundary, as well as the boundary itself. This is a closed region. A region is open if it consists of its interior points, but not its boundary points. This is an open region. In this first graph, we have a graph of the equation x squared plus y squared is less than or equal to 25. We can see that the boundary here is a circle, and the circle has a radius of 5. In our second graph here, we have the graph x squared plus y squared is equal to 25. And in this second case, our graph consists only of the boundary of the circle. Whereas in our first graph, because it's less than or equal to, it includes the boundary of the circle as well as all points within the circular region. In our third graph, what we have is the graph of x squared plus y squared is less than 25. In this case, there's no equal sign, and the graph consists of all points within the circular region, not including the boundary. So in our first case, we say that we have a closed region. This first graph is a closed circular region. The second graph is a boundary region, or boundary, which is a circle. And our last graph is an open circular region. A region in a plane is bounded if it lies inside a disk of fixed radius. A region is unbounded if it does not. Here, we're going to look at the function f of xy, which is equal to the square root of y minus x squared. Let's move that up there. And what this looks like is in the xy plane, a parabola. Here, inside, we have interior points. These are points on the interior of our parabola. In this case, our radicand must be greater than or equal to 0, which means that y minus x squared must be greater than or equal to 0, which means that y must be greater than or equal to x squared. In this case, our interior points satisfy the condition that y minus x squared is greater than 0. That is these interior points here. And the parabola itself satisfies the condition y minus x squared equals 0. The outside points on the outside, do not satisfy the domain restriction that we have here, because the outside points are when y minus x squared are less than 0, and in fact, that is not valid. So we can say that in this function, the points that are valid are the boundary of the parabola and the interior points, because these, the parabola itself, are the boundary points. When we have a function f of two input variables, y and x, if it's equal to a constant, then we call this a level curve. The graph of f is also called a surface z, which is equal to f of xy. Let's look at the example f of xy is equal to 100 minus x squared minus y squared. When f of xy equals 0, we have 100 minus x squared minus y squared, and this can be written as x squared plus y squared is equal to 100. So in this case, what we have is a circle of radius 10 at a height of z equals 0. Let's draw this. I'm going to draw the z-axis over here. This is our height. And then with of, let's see if I can, 64. So we're going to throw a 64 in there. So z is going to have a value of 64. Well, if z has a value of 64, we have 64 is equal to 100 minus x squared minus y squared. And if we add x squared and y squared to both sides and subtract 64 from both sides, we have x squared plus y squared is equal to 36. In this case, we have a circle of radius 6. So that means that when z has a height of 64 up here, gone from 0 to 64, our circle has a radius of 6. So we would say our circle would be up here. Okay, so just to make that a little more understandable, we would sort of thinking of it sort of, this is parallel to our y-axis, and this is parallel to our z-axis. And what we have is we have a two-dimensional surface. This is a circle at a height of z equals 64. And each time that we change the height of z, as we move up, we get a smaller circle with a smaller radius. And as we move down, we get a circle with a larger radius. And what we end up with is a three-dimensional sort of surface that looks like this. Or I should say this is a three-dimensional region in space. In our next example, we have a function of x, y, and z, which is equal to the square root of x squared plus y squared plus z squared. The value of f is the distance from the origin of a sphere. Here's our z-axis, and I'm doing just the positive portion of the z-axis, drawing it. And here's our y-axis and our x-axis. To think of this as, let's draw a little box to represent its three dimensions in space. So when we look at this equation here, as we change the value of f, our sphere becomes larger. So our first sphere, say, could be here. And then as we increase the value of f, the sphere becomes larger. In other words, the value of f is the radius of the sphere. The points in the region x0, y0, and z0, or sub-zero, these points are points within the three-dimensional region. So when working with functions of several variables, we're able to represent both two-dimensional surface and three-dimensional regions.